Please welcome our next speaker, Yuri, who's going to tell us a little bit about software-defined nanosatellites. Interesting thing, me and Yuri actually know each other from the iOS community. He came here to work in Bulgaria, and today was actually the first time that I met him in person. So please, a big warm welcome to Yuri.
Hello.
Wow.
Okay. Hello. As already explained, I'm Yuri. Despite my name, I am Brazilian. So I work at Endurosat. I work as a software engineer from the ground segment, and I also work as a mission operator. So I help with developing the software that operates the satellite and also operating the actual satellite. I'm gonna talk about some part of the work that we do, but first I'm gonna give a very brief company overview, what we do, and then a little bit more technical part. So this work is the development of an operation of a software-defined satellite. And at the Endurosat, we do a lot of different cool stuff. And the goal of the company is that we are ensuring a better future by securing affordable access to space data. This is the general goal. And the company was founded in 2015. We have offices now like in Bulgaria, which is where the main development is, France, Germany, Italy, and the sales office in the US. We have been developing components first, and now we're working on developing complete software platforms. So what this means is that we have like a software, we call this software defined, is that all the components, they are off the shelf, they are easily configurable, but everything else is defined by software. So you only need to input your parameters for your company or your payload, and you can get it working directly. And we're working right now, for example, on adding our constellation services, in that we will have more than one satellite in orbit or working together. And the idea is that we go from the entire chain. So we do payload integration, we do functional testing, register, like ITU registration. We give you the part of the radio frequency spectrum that you are allowed to do, and we also do integration with the launch provider. So you're going to be registered, you're going to be launched, and then we will also do mission operations. So we'll be able to operate the satellite, and you can do it very easily. You can go to the website, you select exactly what is the scope of your mission, how many satellites you want, you select when do you want to be launched, and then afterwards, after your launch, you receive your data. So we do have like a flight heritage. The idea is that we have already several satellites in space, and we have them working. So we have delivered to customers, like to specific companies or countries, different modules, and which is the system in orbit. And we have delivered also complete satellites, which are collections of most of the modules and the entire subsystem. And one of these pictures, for example, was taken by one of our satellites. This is taken by Platform 1. And we have downloaded a lot of data directly from it. And this is using slightly bigger than the satellite that you saw outside, which is using a 6 units called Toolset. I'm going to explain it a little bit later. So you can see on top left, these are the solar panels. So we develop all the modules. Each one of these are components and also structures. So you have power, communications, we have antennas, we have onboard computers, we also have payload computers. So you can operate the different kinds of payloads that you want. You can run code in space, and we also have the web interfaces. So we can download data directly from the satellite. We download the health checks, we download telemetries directly. We have customer requests, which is for example, they tell us, I want a picture over this region of space, or I want a picture over this region of Earth. I want to run this test over my payload. So these are the requests that they execute. And we also integrate with different ground station providers. So we have our own ground station, for example, in Plana, and we integrate with ones that are like in the UK. We have one that is in Svalbard, close to North Pole. We have stations in Italy and looking into other different sites. So some of these are the graphs are data that we actually got from the satellite. So you can see the average voltage of the electrical power supply. We have stability of the ADCS is the altitude determination control system. Temperature of the solar panels, you can see that it varies widely. You have one the side looking to the sun or closer to the sun is always going to be hotter than the other side of the satellite, and this changes depending on the orbit. We have a lot of cool stuff. GNSS antennas, UHF, VHF antennas, X-band, S-band. These are some of for these kind of CubeSats, which are called. They have been developed in the late 90s by a professor from the US. We have the smallest one, which is called 1 unit, the 1U. This is like a 10 per 10 per 10 bots. You saw on the outside, it's a 3-unit satellite, which is the third one. And for example, the pictures from the previous slide were done using a 6U satellite, which is the fourth one. And we also developed the ones that go even higher. We have now a 12, 16, and the S class, which are even bigger satellites. And you can see that these can be tailored depending on the actual thing that you need to do. So if you need to take pictures of space, you're gonna have a different kind of size that you want to use. If you want to use radio modules, if you want to iterate very quickly, everything is very easy to actually integrate. So we have, like, for example, bigger constellations that are going to be working for the Balkan regions that are going to be launching by next year, and they're going to be on one of the higher classes. And we also have the smaller ones, which are using, for example, for radio communication, which are using for astronomy, which are also going to be launching next year. And currently we have ones that are testing electro thrusters in space. They are also doing the code in space. So one of our customers is running their own scripts. And yeah. So we have a lot of successful customers. You might recognize a few of one of them. IBM Space is the one that is owning the camera one. The 6 units one that they run their own code in space. We have Satellite, which runs, they developed their own radio modules for communication. We also have ESA. There's our products that are directly connected to ESA, and they are like for the bigger Balkan constellation. So they're going to be taking cool, interesting features and directly connecting them to the Copernicus missions, the Copernicus service that they offer. Most of some of the customers are like universities because the modules are easy to integrate and you can do very fast prototyping. So if you need to have a mission that is launched very soon, let's say we can do it in 6 months, depending on your requirements. So I want to test, let's say, my thrusters. I want to test my radio. We integrate it to one of their platforms, and it is there in space generating the data that you need very quickly. These are, again, some of the other pictures that we took recently on the platform one, which is the mission that is operated by IBM. So they just have to tell us, we need a picture, and we need the picture over this period of time or over this region of the globe, and we just have to. So, one of the challenges that the space industry faces is that it is kind of limited in sometimes the integration and the launch. So if you want to have a very quick prototype, it's not so easy to get what you want, even if you already have everything set up. You have the launch, you have the radio frequencies spectrum set up for you in less than a few years. So we want to improve upon all of that. So we do the satellite payload integration up to the launch. We want to improve the limited connectivity that you get, because these are very low bandwidth radios that you have communication with. So you generate a little data and you cannot get it enough that is actually competitive. So we go from higher connectivity, we improve from traditional mission operations that require a lot of uptime, which are a lot of people doing. You operate your own satellite very easily. You can just either do it somehow automatically and also do it over APIs that we do online. And we also developing a complex data market. So you want to put it. So you're just going to be able to say, I have generated this amount of data, put it on the store, and other customers or other people can just download them very easily. And three of these solutions are the space ops, which is how you operate the satellites, fully online, the space dev, which is used to develop a component, and we also integrate directly to the modules, and the space store, which is coming up, in which you can just go into the website, you can say, I want this kind of data, and you can download it. So I'm going to be talking now about the space dev and the space ops, which are the part that work on the ground that tells you, I have defined something that will be talking to my satellite, and I can just connect to it and talk. So the space ops is the web interface that we do, and it has orthomechanic modules. It handles the different ground stations, and it also handles the different commands that you send to it. So each one of these commands, we use the same interface that we do on the satellite. We do develop the ground, and they're all shared together. They're all shared. So you integrate online. You just have to connect your module, and you will get instant connectivity to it. The space dev is a desktop application that we use to connect to the satellite. So the idea is that it will be very easy to just do integration. And these they talk to the satellite over USB or over radio. So you have both of these capabilities. It requires minimal setup. You literally just have to install it and start connecting to it. All the available collector commands, they are synced to your cloud, to our cloud. So they are available over API, and you can just instantly start communicating with it. And we have full dashboards, so you can keep sending the same command over and over again until you get the response, or you can do grasp. And it is compatible with all the Toolset modules and platforms. So from the space dev, you also get the full documentation and what you need to actually run the telecommands. So they will be they have like a calibration factors. They have the actual format that you need. You just have to use this. You just have to download the messages that we sent through, and it will all already be set. So you can see here that one of these, they are connected over RS485 directly to one of the components, one of the modules, and you just need this small component to talk directly to it. And you can also connect one of these to one of our ground stations, so you can connect directly to the actual satellite. So we have, for example, we call them flat sats, which are a different kind of mock-up for the module. And we just have to connect one UHF, which is the UHF that goes inside the satellite, and one UHF that is the ground station one. So we connect to the ground station one, and we send command over radio to the actual satellite. So it's literally the exact same thing that we were doing if we're doing space operations. We don't have to have a different setup for on the ground and on space. We just connect them to the exact same way. And they're talking and using the same structure. You just have to click and forget about it. Now, I'm going to talk about the Endursat protocol stack. This is the more technical part of the presentation. So this is the stack which we use to communicate with all of the modules. It goes into radio, and it also goes into those components. So this is a short diagram about it. It's mostly separated. I'm not going to go into details about it, but it's mostly separated into the functional protocol and the command protocol. And you have stuff that you can communicate directly between each modules. So every time that they're stacked in a way that they can communicate. They can communicate over the same interface, the same bus, and one of them just have to follow the same process. And to actually use this code, to actually make this the software-defined part, is that we use a lot of code generation tools. So one of them that we make is that they all have to, we define an interface, this is using a DSL, a specific language that we have made just for talking the messages between the satellites. And this code tool generates code in different languages. So we have Python, we have JavaScript, we have C, we have LaTeX. The Python one is used for QA, so the quality assurance guys use it for use of automation. C is what is actually put inside the satellites. So we just have to define an interface and they will get, they can already use inside the satellite. The JavaScript one is used by the API and the web parts of it. So you have something that is used on the space dev, which you connect directly on the modules, and the space up, which you connect over the internet. And LaTeX, which is generating the documentation about it. Okay, so the C output, maybe slightly mistake. The third element is not exactly true here, but this is how you actually interact with all the modules. So this includes all the messages and is just developing straight away. You only have to put your interface and it will generate the code that you need for it. Python one is used by QA and automation. It is only used because it is very easy to actually make an automation for. So they should have to connect to the models, and most of the testing will be done mostly automatic. If they need to have something functional about it, they can just keep sending the messages and receiving and expecting the different outputs. And one of the other cool things is that it just generates the documentation that it needs for it directly. So if you write something there and how each one of the functions should interface, they're just going to be outputted directly for what you need. So this is actually what each module we get out of it. The JavaScript part is the one that is used by the space ops and the space dev. And these generate a JSON structure, which tells us how we should display this actual information. So on the top part there, you saw the actual bytes, the message that we got from the satellite. And on the bottom, you see a nice representation of what each part of it should be. So you can either see it as a specific format, you can just get the JSON out of it, and you can also just get it in a hex representation for it. So you can see that we get the data in a byte format, in the binary format, and we can show it the way that we want, the way that is more relevant for you. So everything that goes and talks to the satellite has to go to the same structure. So we send it a JSON, we receive a JSON, and this parser changes them from one to another. So we get a JSON, we get a byte output, and vice versa. We call this tool macchiato for some reason. We do not like coffee. But we have like different alternatives if you might already be similar to one of those. For example, these guys from SatNox, which is a amateur radio operation, they use these kite structures, which are done using IM files. And they use this to do the exact same thing, but they only do it in one way. So every time that the satellite that registers on the network receives a byte array, they convert them into an output or into the actual message using this output. But this is only useful for one way. So they only actually decode data from it because they're only interested in that part. And these two, kite was done only for reverse engineering. So it's only on one way, and even though it is actually really good for writing, because you might already be familiar with YAM files, and you can just they're native text files, and you can input them directly. The other alternative is XTC, which is an XML-based format that is developed in the 80s by space agents. And this is, for example, when ESA wants to talk with NASA and they want to have like their same satellite being controlled in the exact same way, they only have to write in this specification, and each satellite operator has their own implementation of it. So they write this specification, they use it for sample integration testing, which is the part before it reaches space, and for the operations, which is doing the same principle that we're showing here. But this is a very inflexible. This is an XML structure that you have to adhere to, otherwise you will not get anything that you can communicate with it. So, for example, if you make a single mistake and if you forget a single attribute, you will not be able to actually parse it. It is very strict and also not strict enough in that you can write the custom attributes, but the standard itself is actually gigantic. So there is over a 200-page PDF that you have to adhere to say that you support fully XCC. And of those features, most of the people do not actually use most of them because there is no most satellites do not actually need all of these features. So this is also not useful for generating code that goes inside the satellite because it only meshes with the actual message. So you cannot input actual useful data that you'll be able to generate code that goes directly to it. So this is used mostly on the ground, but then it's hard to actually make it go inside the satellite. And one of the other parts upon it is that despite it being an open standard, there are no actually that many open implementations. So, for example, the only good one, let's say, only supports like half of the features, and it is sold by one of the actual writers. So one of the guys who work on the standard tried to sell the advanced features on a separate thing on his company. So it's slightly different. And if you go to any open source alternative to it, they don't actually even input them as XML files. So they just take them as if they were text and they process for the text. So they don't consider the actual code, generate the actual code that goes inside it. And what are the advantages over Macchiato, which is the one that we use in Toolset? The advantage is that it's very easy to make a new parser. So we have the JavaScript, we have the C, we have the Python, and each one of these, they're shared features that we can just very easily pick from one another and then use from this base language to generate something that is more interesting. So, and over this, you get the full control over the results because then we can input everything that's related to the ESPS stack. It's directly there, and we get full control of what goes for each message. And the biggest problem, of course, is that since you're writing on different languages, you have to keep the parsers consistent. So each one of them, despite having the specification, they also have to be tested. The actual output of each one of them is consistent, and you are getting the same thing every single time. One of the other things is that it is a Java architecture that is directly made for Eclipse. So you are having to pick and always use it to actually get a usable generator of it. It's based on only a single ID. So you cannot make easy extensions. And I think that's it. And I have more extra slides, but questions? That's it. That's it. Yeah, that's it.